Okay, this is Dr. Williamson going over a problem, and it says the kinetics problem. It says the rate law for the general reaction A plus B plus blah, blah, blah goes to C plus D plus blah, blah, blah. So we're just taking a simple one where we just have two reactants going to products. And then it says explain the meaning of K, lowercase k. B, explain the meaning of lowercase m and n. And you'll notice here that I put these little, they're called carets, these little up caret symbols. Okay. And what that means is sometimes when you're texting or typing in a software program that doesn't let you do superscripts for things to a power, this little caret right here, A caret M, is code talk for A to the M power. And B caret N is code talk for B to the N power. So the program I'm using here doesn't let me do superscripts and subscripts conveniently. Kind of like texting on your phone won't let you do it conveniently. So anyway, explain the meanings of M and N. And does M equal A, this little coefficient here? Does N equal B, that little coefficient there? Explain. Then it says if the reaction is second order in A and second order in B, and the time is measured in minutes, what are the units for K? All right. So I'll come back to explain the meaning of K, the rate constant, in just a minute. I'm going to jump to B first. Explain the meanings of M and N, and does M equal A and N equal B, and explain. All right. First off, no, M is not equal to, like if this A was 3A plus 4B, that does not mean M is equal to A and this is equal to 4. Okay. They're independent of each other. And the values of M and N are determined experimentally and do not come from the balanced chemical equation. Okay, so you need to memorize that fact, right? M tells you how the reaction rate varies depending on how you change the concentration of A, and M tells you how the reaction rate varies depending on how you change the concentration of B. Remember, we're talking about the collision model of chemical reactions in which chemical A and chemical B, remember, we're just talking about A collides with B to make products. So A and B have to hit each other often enough, hard enough, and at the right angle to make products. Often enough means we have a high enough concentration, because a high concentration means frequent collisions, right? Hard enough means at a high enough temperature, because the higher the temperature, the harder the collisions, because the particles are moving faster. It's kind of like cars. The higher the speedometer, the faster cars are moving. And if they collide, they're going to collide harder. We don't want cars to collide, but you guys get the idea. And then a catalyst, I talked about this and taught this in class. A catalyst lines up the reactants A and B in such a way that they collide at the right angle to have the optimal collision angle so that they react the best. Okay, so the meanings of M and N tell you the concentration dependence of the reaction rate. For example, if M was equal to 0, that means no matter how you increase the concentration of chemical A, the reaction rate would not vary at all. You could double the concentration of chemical A and the reaction rate would not double, wouldn't change at all. The reaction rate would not depend upon chemical A at all. Same thing if N happened to be equal to 0. If M happened to be equal to 1, remember this stuff has to be determined experimentally, but if M happened to be equal to 1, that tells you if you double the concentration of A, you would have 2 to the 1 power. If you double the concentration of A, the reaction rate doubles. If you tripled the concentration of A, the reaction rate triples. That's what M means. Same thing for N if N happened to be equal to 1. By the way, if M is equal to 1, that does not mean N has to be equal to 1. They're independent of each other. Okay? If M happened to be equal to 2, that means if you double the concentration of, let me do this just to kind of make it clear. If M happened to be equal to 2, let me put that in red. Okay? If M happened to be equal to 2, if you doubled the concentration, the reaction rate would quadruple. It would be 2 to the 2 would be 4 times. If you tripled the concentration of A, the reaction rate would be 3 times 3, which would be 9. The reaction rate would be 9 times as fast. That's what M and N mean. Okay? Same thing if N happened to be equal to 2. Okay? All right, that's what that stuff means. Let me erase this. Okay, these are the most common values for M and N that you're going to run into, at least in, Chem 1B class. All right, not necessarily in the real world. Next, explain the meaning of K. Well, for the collision model, we had here, the molecules have to collide often enough, concentration, hard enough, and at the right angle. This K is called the rate constant, and it has buried inside of it the temperature dependence and the effect of a catalyst buried inside of it. The rate constant K is given by this equation, A, where this A is called a pre-exponential factor. Pre-exponential factor. There's my mouse writing. And it tells you, it's basically how often the molecules collide. And this E to the minus EA over RT is has buried in it the temperature effect, and the effect of a catalyst. I'll explain that in a moment. But if we change the temperature of a chemical reaction, if you increase the temperature, generally the reaction rate will go faster. And the reason for that is you will actually, if you change the temperature, you will change the value of K, the rate constant. And if you change the value of K, the rate constant, you then change the value of the rate of the reaction. So that's basically that for now, for this part. Next, EA, that's the activation energy. Remember, I said they have to collide often enough and hard enough. To collide hard enough, they have to collide hard enough to break chemical bonds. Well, how hard is that? That can be measured in what's called the activation energy. How hard they have to collide to break these chemical bonds so chemical A and chemical B can react is called the activation energy or activation energy barrier. And here I made a reaction coordinate diagram that shows here the reactants, A and B. Over here, I have the products, lower in energy. Reaction progress goes this way. Here, this is start. This is finish. So this is the reactant. It's turning into products. To make A and B turn into products, they have to collide hard enough to get over this activation energy barrier. And in this example, they have to collide with this much activation energy. How much energy is that? It's not the 50. I made up these numbers. It's not 50 joules per mole. It's not 300 kilojoules per mole. The activation energy is going to be the difference between these two in my made up problem. 300 kilojoules per mole minus 50 kilojoules per mole. That's going to be 250 kilojoules per mole. So without a catalyst, these things are going to have to collide with 250 kilojoules per mole of collision energy to break the chemical bonds of A and the chemical bonds of B so they can make the products. And that's this activation energy right here. If I use a catalyst, and I've taught you guys how catalysts work before, a catalyst finds an alternate reaction pathway with a lower activation energy barrier. So if I have a catalyst, this will be EA cat. Catalyst finds a way of making A and B line up just right and collide at just the right angle so that it doesn't take 250 kilojoules per mole of energy to break their chemical bonds, but actually takes less energy to break their chemical bonds. And in this example, it lowers the activation energy barrier from 250 kilojoules per mole to 225 minus 50 down to 175 kilojoules per mole. Again, these are made up illustration numbers. Okay. So a catalyst lowers the activation energy, finds an alternate reaction pathway that has a lower activation energy barrier, and that helps the reaction go faster. And that effect, this value of lower activation energy barrier, is hidden or buried in K, the rate constant. So the rate constant K has buried in it the effect of temperature and the effect of whether or not you have a catalyst. Because if you lower the activation energy barrier, that's going to affect this equation right here, which affects K, the rate constant. This capital A right here is not the same thing as this A chemical reactant. It's just coincidence. Okay. So that's the meaning of K. It's actually kind of a lot. Next, it says if the reaction is second order in A and second order in B, and time is measured in minutes, what are the units for K? So let's solve that. Let me erase this stuff. Hopefully without erasing everything else. Oh, I did not intend to do that. I'm glad I got that got that undo function thing. All right, so let's kind of clean this up a little bit. So if it's second order, it means R equals K, A, second order, B, second order. That's what it means in this example. And time is measured in minutes. That means, and remember, the rate is typically the rate is going to be molarity per second. That's what we've seen frequently so far. But here, the rate is going to be molarity per minute. So I'm going to substitute these things in. First, I'm going to solve for K, rearrange the algebra for K. K will be equal to the rate over A second power or second order, so squared, B, that's second order. And then I put in the units. This will be molarity per minute. A has units of molarity, and that'll be molarity squared. B has units of molarity, so that'll be molarity squared. So K will have units of, let's do this here now. This will cancel with one of those. So I will have 1 over minutes and I will have molarity squared times molarity. Molarity squared, and that's on the bottom of a fraction. Well, that's actually, on the bottom of this big fraction right here, right? You guys get that? So that's going to end up K. Let me make a little bit of space here. Erase this and I'll put it over here. Well, I could just do it right here. I'll end up with K is equal to molarity, the -3. Let me make that -3 more clear, to the -3 minutes -1, right? So then K, and I could, if I were to type it, just kind of show you guys this, right? I could say, if I were to type it, let me do it in a larger font here, 12, let's do 36. K has units of molarity, and then how would I type it? The -3, see that up, caret, minutes, -1. ellipse, and that is, I would do that part. Okay. So that was kind of a long, detailed explanation, but that's how I do that. And I'll do more problems for you guys later, but this is all stuff you want to have in your head for the test. Okay, then. Hope that helps.